Hi guys, welcome to the second lecture on TensorFlow for deep learning research. Again, we are going to be following the CS20 SI class which is being offered at Stanford this quarter. So thanks a lot to Stanford and to Chip Huyen for making the slides public. We are going to be covering basic operations, certain tensor types, placeholders, and lazy loading in today's lecture. So a lot of very important concepts. So let's get started. If we look at our first TensorFlow program, we are importing TensorFlow. We are defining A and B as tf.constants and with a lowercase c, and we'll talk about what's happening out there later. We are not specifying any name arguments out there. We are adding an op x, tf.add a comma b. We are opening a session and running x. So this stuff we covered in our last lecture. This should be familiar as of now. The new thing we are going to do out here is to visualize this graph using TensorBoard. So how do we go about doing that? It's actually very easy. Google made it really easy. What you do is after you create this session, so you need to have the session context, you will just use this line, tf.summary.filewriter, and you will specify a location where you want those events to go, and you will provide what you want to write, which is ses.graph. So every session will have a graph on it. We already talked about that earlier. In the tf.session, if we don't specify any arguments, it will take the default graph, or you can specify a graph out there. But in this case, when you access it ses.graph, the graph which is bound to that session will be put in the TensorBoard event files. Now, when you do print ses.runx, some events will be written to those to this location, and we'll see how to visualize it. And you always want to close the writer when you're done using it. So the way you run it, we run our program the same way we do Python and whatever the name is. And then you issue this command, TensorBoard and ---- log dir is equal to the location of your graphs, and you specify a port. Now you can go to the localhost colon same, it's actually trying to go there, to the same port name, and then we will be able, this visual will come up. When you click on graphs, you will see this coming up. Now, here you are seeing const and const_1. This refers to the A and B nodes out here. We have not specified any names, so TensorFlow will give default names. The add operator also, we have not specified any name. So the default name for the add op in TensorFlow is add, surprise out there. And then we will go ahead and write this line, but I think, well, there seems to be a problem out here, because what we want to do is to have this line after the TF session as ses, because otherwise there is no context of session going on. It will throw an error. So let's let's just assume that this writer is written in the context of the session, which is what we will be doing, and I think that's what was done earlier on. Yes, in the earlier slide, that's where it is. So we'll do that. And when you see, we already talked about, you'll see const and const_1. Now, what you want, you might want some time to make your graph more readable, and you can add in a name argument out there. And once you put in the name is equal to whatever you want out here, and out here you're also, for the add operator, you are giving the name add. The same thing, what you will see are the new names in the TensorBoard. Lowercase a, lowercase b, add, the earlier add was with a uppercase, if you remember. So this is how you start visualizing your graph, your running graph in TensorBoard. Again, really good advice out here. Use TensorBoard. It is one of the best things that has been inbuilt in the TensorFlow framework. For other frameworks like Cafe, you have to actually do stuff to make this happen. Out here, a lot of this stuff is just automatic. So you want to do that and understand how the whole thing works. Now, let's look at the signature of the tf.constant op. So what we are giving out here when we instantiate a constant, when we add that op, I should say, there's a value. You can provide a d type or it can be inferred. The shape can be provided or inferred, and we'll go into what happens. And const is the default name, and as we saw, that's what TensorBoard was putting in the visual. And if you have more constants coming in, TensorFlow is smart enough to make sure that these names are unique. And verify shape is by default false. So what verify shape does is if you provide a value and a shape, and let's say if you were to do verify shape is equal to true, it will throw an error if the value does not match the shape which is provided. And if it is specified as false, TensorFlow does something interesting. It will just repeat the last value. So let's see what's happening out there, just to make sure we are all on the same page. So let's say a is equal to tf dot constant 2, and let's say shape is equal to 2 comma 2. Okay, and I say verify shape equal to true. I want to make sure that this needs to be 2 by 2. This will give an error that the expected shape is 2 comma 2, and I got a scalar out there. But if I do the same thing and I have the default which is false, or I can just remove it, this is what shows up. And if I were to, okay, so by the way, if you want to run everything in interactive mode, we just say tf dot interactive session, and now there is a default session which shows up. And now if I want to evaluate a tensor, remember everything in tensor, all the ops are just ops, which are points on a graph. When we want to actually get the value, you have to use a session and run it within that, or alternatively you can if you are doing it in an interactive way, we can just create this default session, and now if we do a.eval, it should show up. So now, even though I defined a constant out here, a scalar, but the fact that I put in a shape 2, 2, the last value gets repeated. Now, if I were to do b is equal to tf dot const, let's say 2 comma 1, and then I do shape equal to, let's say 3 comma 3, and remember the verify shape is false, so it's going to just repeat everything, so repeat the last, which is the 1. So that's how it will look, b.eval, and this is what happened. So it took the 2 1 and then it got the third dimension going, right, 1, and then it just repeated that last number. So just this is an interesting functionality that is available if we need it. Okay, so that's that on constants. So what you can do out here is you can create out here, we are creating a vector, naming it A, and again, this is the signature out here. B is again another B is a matrix out here, and it's a different dimension, and now I can add the A and B. So interestingly, there is a broadcast that's going to happen. So let's see what happens out here. If we were to, once we define the constants A and B, and we put in the add op, A comma B. Now if we were to do x dot eval, what we see is that the value of 2 comma 2 is broadcast to this other matrix. So what does that mean? So now 2 comma 2 gets added to each of these rows. So the first element becomes 2 comma 3, the second element becomes 4 comma 5. So there's a broadcast happening, and this is similar to what you see in NumPy. Now let's see what happens if we try to multiply A comma B. Now this is an element-wise multiplication, and what happened out here was 0 comma 1, 2 comma 2 got multiplied to both. So that becomes 0 comma 2 and then 4 comma 6. So this broadcast is basically the same that you would expect if you are used to NumPy add and NumPy mul. Okay? And the creation of the constants is also the same as you do in NumPy. And as we go along, I will show certain pitfalls where things that you might not intuitively expect happen, and how we can use NumPy to get around that. Now tf.zeros and tf.ones, very important when you want to create tensors and which are pre-filled with certain values, right? So for tf.zeros shape, dtype tf.float32, what happens is it will create a tensor of this shape, and it will fill all the elements with zeros. Now again, this pretty much goes without saying in every op with TensorFlow, where when you write that statement in your code, in your graph, nothing's gonna happen. The only time when things really happen, the memory gets allocated, the zeros get filled in, is when you run this op within a session. Okay. Example out here, tf.zeros, you give in the shape what you will get when you run it with session, or if you have interactive session, you can just call eval on this tensor, you'll get this matrix. Now, if you do have some input tensor of some shape, right, and you want to create another tensor of the same shape and fill it up with zeros, what you would do is you would call the op zeros underscore like. So what happens is, let's say if we have an input tensor which is a 3 by 2 matrix, right, and we put in the op tf.zeros like input tensor, you will get a tensor of 3 by 2 shape filled with zeros. So it just, and you will see as we go into some of the models why this is important. And even though you can, given an input tensor, you can always get its shape and use this, we'll get into reasons why this is something which is preferable. Again, there is a direct map from numpy.zeros like out here. So for zeros, tf.zeros, for ones, you would do tf.ones. And remember this argument tf.float32, if you give, it's 1.0s that are going to get filled up. So it's a float32. If it's tf.int32 or any of the other int variants, it's going to be an integer value of 1 that's going to get filled. And as we saw in the last lecture, TensorFlow does this type matching, so type checking. So we want to make sure that we have our types right. Once like has the same concept as zeros like, where given an input tensor, it would fill it up with ones. If you want to, instead of zeros and ones, if you want to fill it up with some other value, then we can use the call tf.fill. You put in the dimension, so you can put in the shape and the value, and this is this is what gets filled up. So the important thing out here is that the value is a scalar, right? So you create a shape, put in a scalar, and you get back a tensor with the shape, with the dimensions, and the value, the scalar value that you provided. And I would really advise you that if you are watching this, then have a session, Python session open, very similar to what I have out here, and try this stuff out, try typing this stuff in, because what happens is as you do this, it will develop a weird muscle memory, and that's important. Otherwise, you'll spend half of your life on Stack Overflow or on the API documents. So it's good to get a little bit of the muscle memory going out here. Okay, so let's talk about some other types of constants. So there are a lot of sequences that we can support in TensorFlow. One of them that you'll be using quite a bit is tf.lengthspace, where you start and stop at two different numbers. And here, one of the differences with the NumPy version of Lengthspace is that start and stop out here are supposed to be floats, so either float 32 or float 64. And you will just get the number of equidistant intervals out there. So for example, 10 to 13, 4, you will get 4 different floats, and they are all spaced equidistant. So that's tf.lengthspace. We have the tf.range, where you start with a number and go to the limit, but you don't include the limit. And delta is the step size. So for example, if start is 3, the limit is 18, and delta is 3, we would keep on going as many numbers as required to get to the number right before the limit, which is 18. So you'll just get to 15 out here. If you just provide tf.range with just an integer limit, it works exactly like the range in Python, where you would start from 0 and go up till and not including the limit. Another important note out here is that in Python, if you're looking at just the normal range that you can use in Python, you can always iterate over it, but in TensorFlow, tensor objects cannot be iterated over. Now we get to randomly generated constants, and you'll be using them all the time. So whenever you have a model that you are trying to, and you have some variables that you define, some parameters, you'll always be initializing them with some version of these. So let's just go through all of them. So tf.randomNormal, which is you provide a shape, and it just samples from the normal distribution with the mean that you provide, or 0.0. Standard div is 1.0 out here, and the default t-type is tf.float32. So this just gets samples from a normal distribution. tf.truncated normal is kind of the same, but the only difference is that it is denser, in the sense that if it samples a number which is more than 2 standard deviations away from the mean, it will drop that number and resample. So it just makes sure that whatever sample you get, the shape size sample, is always going to be within 2 standard deviations of the mean. Random uniform, we are sampling from the uniform distribution out here. Random shuffle is you take a value is going to be a tensor, and you are going to be shuffling on the first dimension. So let's just go through it. Let's say we have a tensor which is a matrix, which is a 3 by 2 matrix, and we call tf dot random Now, when we have this, we can always run eval on it because I have the interactive session running. And in this case, it has not shuffled anything. It is just the same, but it's random. So it can, the next time it is shuffling. And that is the functionality that you get with random shuffle. Now, the only thing to notice out here is that it will always shuffle on the first dimension. And it is it's useful in cases where you take a data set and it might be a data set of images. Now, images might be, let's say, 28 by 28 by 3 is one image, right? And you might have n such images in a batch. So when you call tf.randomShuffle, it will do the right thing and just shuffle the images on the first dimension, which is the batch. So pretty useful. tf.randomCrop. So out here we are providing a tensor value, and you are also going to provide a shape, right? Now it's going to crop out a contiguous block of shape from the tensor. So what does that mean? So if we are talking about, let's say, a lot of these, it might be a good idea. We can go through it right now, but just know that they exist, and when you need to use it, you'll have to go to the TensorFlow API docs and really see what's happening. But to give you the general idea, shuffle, if you're looking at images, will just shuffle on the first dimension. The random crop will randomly crop a contiguous block of shape size from the images. tf.multinomial. This one is interesting, where you provide logits, and when you're sampling, you will be sampling. Go through an example to understand tf.multinomial a little bit better. So let's suppose we define a tensor which is np.random normal size is equal to 3 by 4. So it's a 3 by 4 sized tensor, and we are sampling from the normal distribution. We assign it to B. Now, if we were to do, so when we do a tf.multinomial with the tensor B, and let's say num samples is 5, what we see is this array. Now, we might think that, okay, where is this coming from? Because B is all these numbers. So here's the interpretation. So this tensor is being interpreted as a logit. So in logit, what you'll have is some number of batches, which in this case is 3. And then there are the number of classes, which in this case is 4. And the classes go from 0, 1, 2, 3. So for each of the batch, right, we are going to be sampling 5 times from this distribution. Okay, this unnormalized distribution. So what you would assume is, since out here this is the biggest number, most of the time when I'm sampling 5 from this distribution, I should be getting 3, and which is, well, in this case we are seeing 0, 1, 2, and this is obviously this is a random sampling going on, so that's what you'd see. Now in the second case, we are seeing the biggest number is 1, so we should see mostly 0, which is what we are seeing. And similarly in the third case, the only non-negative, I guess, is the 3, so we'll see that. Now if we increase the size of the sample, we should probably see a better distribution, let's say. Well, better is relative because it's just random. And you'll see that, okay, out here many more zeros, out here more ones probably. Well, somehow this keeps on liking the 0, 1, 2, but again, you get the idea. Random gamma is, in statistics, it's another distribution which has 2 parameters. One is the shape parameter and one is beta. Now, the shape that I just talked about is not this shape. This shape is the TensorFlow shape. So the parameter we are talking about is alpha. Let's just look at some examples out here. So what happens out here is if you were to call tf.random gamma and provide a shape of 10 and an alpha value of 5, we are going to be getting the shape number of samples for each of these alphas. So out here we are getting a vector of 10, so that's the size you will get for the alpha value of 5. Now if I were to do 10 and provide a vector 5 comma 15, right? So now I'm providing two values of alpha. So what I would get is 10 by 2 samples. Now the first column is going to be with the alpha of 5, the second column is going to be with alpha of 15. Okay, so this is exactly what we are seeing out here. We are getting 10 by 2, so the first column out here alpha of 5, the second is an alpha of 15. So that's another interesting and useful distribution that you might come across. Okay, so if you want to be using a lot of these randomly generated constants or sequences, it might be a good idea to set the random seed for the whole graphs. And the way you do that is tf.set_random_seed, and you can provide 0, 42, whatever you want. Now, once you do that, things are going to be deterministic in the sense that if you run your experiments again, these values are still random, but they are going to be more deterministically random. So you can at least repeat your experiments and you won't be left wondering why one result is slightly different than the other. So it's usually a good idea to do that when you're trying to build your model and initially test your models out. And you can do this after you set up the graph. Before you are calling the session.run, just set this up once and for all, call it. It's an op, so you'll have to call it, and then you're done. Okay, so this is just a slide from the operations that are available, and again, it's a good idea to just go through them and take a look at them, but usually what will happen is when you actually need to use them, you'll have to go look at the docs initially, and then once you get comfortable, it's going to be very easy. Okay, so some operations out here that we can go into. We are generating a constant out here, a, b, element-wise addition, so 3 plus 2, 5, 6 plus 2, 8. Again, I don't want to sound like a broken record, but nothing is going to happen when you do that. You'll actually have to call it with a session.run. Now, another API for addition is available, which is the tf.addn, where you can provide n arguments out here in a list, and all of them are going to be added. Mul is element-wise. Matmul is a matrix multiplication. So A will need to have a dimension of, if A is m into n, then B has to be n into m. And if it's not so, it's going to throw a value error. And matrix multiplication is not commutative. So A, B is not equal to B, A. So same is the case out here. tf.matmul AB in general is not going to be the same as tf.matmul BA. For if you want to really multiply in B, you'll have to reshape this to the shape out here so that you can go through the multiplication. Div, what you would think, again element-wise, AB, 3 by 2, 1, and obviously it's an integer, so it's going to just floor it. And 3 out here, mod is the same element-wise. So this is some of the basic ops. You'll be using them all the time. Okay, so some of the native Python types, booleans and ints, floats, strings, etc. are understood by TensorFlow. So you can come up with statements such as t0 is equal to 19, And if you say zeros like t0, so if you remember from previous lecture, we are looking at the size shape of this and the zeroness of that. So 19, the zeroness of that would be 0, so you would get that. And similarly for ones, 0 and 1, the t0 is the shape, is out here is scalar, and then we are going to be getting 1. Now, so this is interesting. So if you have a vector of strings and we come up with an op which says tf.zeros like this vector, what do we expect? So if we think of, can we come up with a zeroness concept for strings, it's probably going to be empty strings. The shape is well defined, which is just a vector of 3, so we would expect a vector which is, the shape is 3, a vector of 3, and it is an empty string. But if you were to ask tf.ones like t1, then we won't be sure as to what the concept of 1 is for a string. So TensorFlow is going to get confused and it's probably going to throw an error, right? Just like what it's doing out here. As far as Booleans are concerned, Booleans, if you have a matrix, the way it is defined out here, then the zeros are well understood, 2 by 2 tensors, because the shape out here is, actually it's going to be 3 by 3. Yeah, so it has to be a 3 by 3 tensor, and all elements are going to be false, and ones, which is going to be 3 by 3 tensor, and it's going to be all elements are going to be true. So that's what's going to happen out here for Booleans. So yeah, there is a problem. There is a slight error with the slides out here. It should be a 3 by 3 tensor, but that's pretty obvious. But the elements are going to be the Boolean values, false or true, depending on whether we are calling zeros like or ones like, because the zero concept or the one concept, the truthiness is very well defined in the concept when we are talking about Booleans. Okay, here are the TensorFlow data types: float 3264, int 8, 16, 32, 64. All of these we use a lot, so just they're out there for you to take a look. Now, TensorFlow, the data types, and in general, TensorFlow plays really well with NumPy. So this, the TF, the int32 is exactly the same data type as np.int32, so that can be used interchangeably. And also, you can, instead of providing the dtype out here as tf.float32, you can provide np.float32. TensorFlow would play well with that. And if, when we are calling tf.session.run with a list of ops to run and fetch, if the return value is a tensor, then what you would see, the output of session.run is going to be a ND array. So that would come back to Python as an ND array, which would be, it would be really easy to print or do whatever you want with it. It's a good idea to just use TensorFlow types, the list that we saw earlier, for tensors, because now TensorFlow would need to go through an additional layer of inference to figure out the Python type. And also, these are two different projects. NumPy is one, TensorFlow is a Google thing, and they might start diverging at one point or the other. And then if you play in TensorFlow world, your code is gonna still keep on working when that happens. Okay, so what's wrong with constants? Well, they are constants. That's a big problem with constants, that they are actually stored in the graph definition. So if you were to print out let's say we define a constant, tf.constant, an array. Let's call it a vector of two floats, and let's say we print out the graph as we print out the graph, and the way you do that is sys.graph.asGraphDef. So it comes back with a serialized version of the graph that now you can print out as a string. And when you do that, and I would highly suggest that you just open up your interactive session on Python and type this in, you'll see that it shows up with the actual value which is stored in the graph. Now, obviously, when this happens, loading of the graphs, etc., becomes very expensive. So what you really want to do is just use constants for the primitive types, and if you're trying to load in images or data, it's a good idea to use variables or readers that we will hopefully get into pretty soon. Okay, let's discuss variables. So you can define a variable, tf.variable, with a value and an optional name, and the value can be anything of any size. It can be a vector, as is being shown in the second example out here. It can be a matrix, or it can be a huge 784 by 10 tensor, which is full of zeros right now. Okay, so the whole idea is that you define a variable and you put in the value that you want the variable to start with, and the size is also inferred from the value that you are putting in. We see out here that tf.constant is, the c out there is lowercase, but tf.variable, it's a uppercase v. And the question is why? Well, it turns out that constant is just an op, whereas a variable is a class, and there are a lot of different functions, different methods that you can call on variables. So we'll go into some of them very, very soon. So if you were to look at, let's say an example, x is equal to tf.variable, can be whatever, let's say 5. Now, there are a bunch of ops that come pre-packaged with a tf.variable. So one of them is x.initializer that we'll be using quite often, the read operation value, x.assign, which is a write op, which would assign a value into x, and assign underscore add, which is it will add the value in parentheses to what is in x and then assign that to x. Now, one thing to remember is, again, all these are ops. So if you add them in your graph, you'll have to call them from session.run for them to take effect. So let's see. One very important thing with TensorFlow is that you have to initialize your variables. You just cannot do anything with the variables unless you initialize them. So the best and the easiest and the most common way of doing that is just using this line, which is just use this construct out there. You define an init function, if you may, init op, tf.global variables initializer, and you instantiate a session and call session.run init. Now this does everything that needs to be done. It will go look at all the variables out here. Let's say if this is the graph you're talking about, and it will initialize the a to the value 2, b to the vector 2, 3, etc. And now at that point, if you were to call an eval on a.eval or b.eval, you will actually get the values 2 and 2, 3 respectively. If you don't initialize these variables, TensorFlow is just going to throw an error. Also, you can initialize only a subset of variables. So this is the construct to do that, tf.variables underscore initializer, and then you just pass in a list of the variables that you want to assign, and then when you call this op, then only these variables are going to be initialized. So why would you want to do that? So it turns out that another way of initializing variables are to assign them, to call the assign op on them with a certain value. So let's say you are training a model and you want to do transfer learning. So some layers of your model, you want to just assign the values from a previously trained model, whereas there are certain other certain other layers which you want to just initialize randomly and then start the training. So you can do things like that by just initializing a subset of variables. So it's sometimes a useful thing. And also, there are various ways of doing everything. So this is one way of doing that. Initialize a single variable is just so, as we saw, that every variable comes bundled with this initializer op. So what if you want to initialize just a single variable, what you can do is, let's say this is the variable w, you can just call session.run w.initializer and it will do the right thing. So what will it do in this case? It's going to create this tensor and fill it up with zeros. So the tensor is already created. It's going to actually fill it up with zeros at that point. The way to get the value of a variable is to call this method called eval on it. For example, if w is a tf.variable and you do want to run the initializer, and the initializer op, as we just discussed, comes bundled with the variable. So once you do session.run w, now if you want to print w, what you would want to do is to call w.eval. What eval does is that it is a short form for getting the TensorFlow will get the default session and then run w on it. So for example, this statement w.eval is going to be called as tf.getDefaultSession.run w. So it's a short form of writing that, and then you can print out that variable. Another op that comes bundled with tf.variable is assign, and it does what you would imagine. It assigns a value to the variable. So out here, if we define w as a tf.variable with a value of 10, and now you do w.assign 100, when you, and again, remember, assign is an op, so that needs to be called in the context of a session for it to take effect. So tf.session as ses.run w.initializer. So now at this point, w is initialized to the value of 10. Now, if we call print w.eval, you would think that since this w.assign 100 has gone through, maybe we should get 100, but we have not yet explicitly called that w.assign 100, so what you will see is 10. And that's what we see out here. So what happened out here is, even though we added this op w.assign 100, since we did not call it as session.run w.assign 100, that value never got changed from 10 to 100, and that's why we are seeing 10 out here. So the way to do this would be, once you declare the variable tf.variable 10, you will come up with an assign op w.assign 100. You would run the initializer, and then you would call assign op on it. Now, one of the things that we will see is that when you're assigning a value to a variable, it is okay if the variable has not been initialized before. So even if we did not run session.run w.initializer, but we ran session.run assign op, that will do the right thing in initializing w and then assigning the value 100 to it. And I guess that's exactly what we are talking out here. we came up with this assign op out here. We ran sess.run assign op, and we did not call session.run w.initializer in this code. And when we do w.eval, it will show you the right thing, the 100. So the initializer op is the assign op that assigns the variable's initial value to the variable itself. So when we are calling initializer op, what is actually happening is that the assign op is being called, and whatever value there was, which is 10 in this case, gets assigned to w. So it's one and the same thing. Now let's see what's happening out here. Let's say we have a variable, myvar tf.variable2. We are calling it, we can always name a variable myvar, and we declare an op, which is myvar times 2, which does myvar.assign 2 into myvar. Now, if we call session.run myvar.initializer, because it's a variable, you have to initialize it. And now, if we call session.run myvar times 2, what happened out here is that myvar is assigned the value of 2 into myvar. And remember, since we ran that session.run myvar.initializer, myvar at this point is 2. And so myvar will get assigned the value of 4 after at the end of this call, my session.run myvar times 2. If you run it again, what will happen is let's just follow it closely, session.run myvar.initializer. It initializes myvar to 2. The second op is called myvar times 2. It takes the current value, which has been initialized to 2, and makes it 4. So myvar at the end of this call is 4. Now we are again calling myvar times 2. So myvar is assigned 2 into 4, 8. So this will get assigned 8. And that's what we are seeing. And it will keep on getting multiplied by 2 every time you call it. So assign add and assign sub are kind of related operations. So let's say if you have a variable myvar tf.variable10, you run the initializer on it. Remember, we always have to do that. Now if we say session.run myvar.assign add 10, what will happen is it will take the value which was there, 10, add 10 to it, and it will show 20. And if you run myvar.assign sub 2, it will take the current value of myvar, which was 20, and subtract 2 from it, and we'll get 18. And another important note out here is that as we talked earlier, assign would initialize the value of the variable, but assign add and assign sub will not, because they do need that initial value for them to take effect. Makes sense. Every session will maintain its own full copy of the variables. It maintains a full execution environment, wraps the whole execution environment and maintains that. So if you have a variable w and you define 2 sessions and you run the initializer in session 1, now in session 1 w is initialized as 10, whereas in session 2 if you run you need to do both of them. Now let's say if you're trying to do session1.run w.assign add 10, it will take the value of w in session 1, which is 10, and add 10, you'll get 20. In session 2.run w.assign sub 2, what will happen is that the value in session 2 is still 10. It has its own copy. And when you do a sub 2, you will see 8. And that's what we are seeing out here. It's very important to remember that, because if we are dealing with multiple sessions, what can happen is if we don't closely see what's happening and following the exact execution path, we might expect something. For example, in this case, session.run w.assign add 100, the value was 20, 120. And sub 50, it's not going to give you 70, which if you might think should be there, but since session 2 has its own execution environment, own variables, it will take 8, subtract 50, you'll get minus 42. And always a good idea to close the session so that you release all the resources. Let's say we want to have a variable and declare another another variable which is twice the value of a variable. So W is a tf.variable truncated normal 700 by 10, and U is tf.variable 2 into W. Now, let's say if this is the situation and you want to run some of these ops. First of all, since both of these are variables, you will need to initialize both of them. This might not be that safe. The reason being that W might not be initialized. So what you want to do is, if you want to do something like that, you want to call w.initialized value. This will make sure that W is initialized before its value is used to initialize U. Let's say we have W as tf.variable2 and we have U as tf.variable2 multiplied by W. And let's say we just get the interactive session and save it as ses. Now we can initialize W, which is ses dot run W dot initializer. Now if we print W, you will see 2, which is all good. Now if we try to initialize U, if we try to print U, you'll get an error because it has not been initialized, right? So what you would have to do is to do initialize U also, and now everything is fine, right? But if you try to initialize, if the example were that, let's say, come up with new variables, A is equal to tf dot variable 2 and B is equal to tf dot variable 2 into A. Now, if I try to initialize B, so we'll get an error because the variable that it is depending on has not been initialized. So to prevent that, what we want to do is to, when we are trying to declare the second dependent variable, you want to call W into 2 into W dot initialized value, which will make sure that W is initialized. In that case, if you call U dot initialize session dot run U dot initializer, it's going to do the right thing, initialize W and then initialize U. So we sometimes see interactive session, and this is something when you're trying to run your program interactively in the Python console that I've been doing, you would just use that. It's just that it makes itself the default. So then once you define ses is equal to tf.interactive session, now this session is the default session for that graph. And at that point, if I have some ops, A, B, C is equal to A by B, instead of doing session.run C, I can, in short form, I can just do C.eval, and what this will translate to is tf.get default session dot run C. So, and the default session will get returned, ses is going to get returned as the default session, and it will evaluate C, and then you can close it. And many times you want to make sure that certain ops have run before you want to run another op. The way you do this is by defining the tf.graph.control dependencies. And let's say our graph has A, B, C, D, E. Now, if you come up with this with context block with g.control dependencies A, B, C, anything that happens inside this block, this will D, E. Now if you want to call D and E, these will only be run after A, B, and C have been executed. So why would we need something like this? So let's say you have a complicated model, a complicated graph, and the initializing is happening, and maybe you are assigning a subset of the variables from some model that was trained before as transfer learning. And now within the graph, you want to make sure that when you're calling a certain operation, those assignments, those loading of the weights, etc., have already happened, and you just want to explicitly make sure that that happens so that there are no weird errors that come down the line. You would use something like this. You would just put in those ops that D and E, they don't necessarily depend on in the sense that it's D and D will still run, but it's just that the errors would be there would be errors. So you do that dependency control by using control dependencies. Okay, let's start discussing placeholders now. So quick reminder, in TensorFlow we assemble the graph and then we use a session to execute operations in the graph. We have covered this before. So the whole idea with placeholders is that we don't really need the data to be in place to assemble the graph and then to start executing some operations within a session. We can assemble the graph without knowing what the data is, and then we can feed in data at a later point in time. So it's analogous to any function that you might think of, like out here, the function is x squared plus y, and we can calculate this function and implement it without knowing the value of x. It's kind of the same concept, where in this case the x and y are placeholders for the actual values that we would be calculating down the line. Again, the whole idea out here is that we or our clients, whoever we are writing the models for, they can supply their own data when they really want to execute the computation. And also, we don't really want to, as we discussed earlier, we don't want to save, like, let's say we are trying to do image classification and the training data has like 1,000,000 images. We don't want all those images to be loaded into our graph for the reasons we saw in the last lecture. So the way we define placeholders is the tf.placeholder operator, and you define the type and the shape. Now, once you have this definition going, now you can use A out here as if we already knew the value, right? So let's say A is the placeholder, B is a constant with the same shape out here, and we come up with an operator C, which is A plus B. Now, if you try to run ses.run C, at this point, TensorFlow will throw an error. Why? Because it does not know the value of A. So what we need to be able to do is, when we are running the operation out here, we need to be able to feed the value. So the way you do it is this argument feed dict, where you would create the dictionary of all the placeholders, and you would feed them within this ses.run call. So the way you would do it is, you'll define a dictionary A colon 1, 2, 3. Now, the important thing out here is that in Python, when we are dealing with dictionaries, it's very common to have a string as a key, but out here we are putting the actual tensor as the key. Okay, very important. It's a little bit non-intuitive when you first come across it. So put the tensor, and there might be multiple tensors which are placeholders. You'll put the actual value of A as just A as the key, and now when you call ses.run, you want to define the operator that you want to run C, and then the second argument would be the dictionary of placeholders, in which case A1, 2, 3, and it will show you 6, 7, 8 the way you would expect it to. Now, out here we defined A with a shape of 3. You could have said shape. Shape is equal to none also, in which case A could have been of any shape. Shape is equal to none means this placeholder can take any shape. Okay. Now, you would think it's easy when you are doing this, but then a lot of ops do need to know the shape. For example, out here, if you were to do shape is equal to none, and B is a constant with a shape of a vector of 3 and you try to calculate the op c, a plus b, it will throw you an error if you had defined a with shape is equal to none, because this operator actually wants to know the shape of the various ops within that. So something to be careful of when you are constructing the graph. Yes, so this is being mentioned out here. Shape is equal to none breaks the shape inferences, and some ops, in this case, if you were to try to do it with add, it would break, right? So when you think of placeholders from, let's say you were to use a tensor board to visualize, they are actually valid ops. They are first-class ops on their own footing. So you would, once you place them in the graph, they would go in the graph, and they are just, you would use them exactly as if you had defined a constant or something similar out there. So important thing, you'll visualize them in the tensor board also. So the way you would feed multiple data points in is when you are calling the ses.run, you'll have a loop with various values that you want to call that op with. And this is a construct that you will see a lot when you are writing real models, because one of the things that you would do is you will define a training op, and when you call ses.run train op, and then you provide a value, let's say one image and its label, right? So it will call the training op with that one image and a label, and I'm assuming that the batch size is just one out here. And you will just, the way you would train is you would just keep on calling this in a loop. So you will just call ses.run. Let's say if you have 1,000,000 images for training, you will just call it 1,000,000 times for one epoch. So that's how you feed in various values. Now, this is an interesting thing in the sense that you can use feeddict for any of the variables or constants in your graph. So, well, the way to figure out whether you can do that or not is a call that you can ask the graph. So you define your graph, and then you can get a handle to the graph and say is feedable and any of the tensors that are defined in your graph. And if the answer is true, then you can actually feed that value in during the ses.run call, even if it is not a placeholder. So in this case, for example, you have a is equal to tf.add and to 5. It's not a placeholder, it's an actual op with real values. And B is using that. Now out here, you can create a dictionary of A15. And now if you call ses.run B out here, it will, with the dictionary as the second argument, it will replace the value of A to 15. And in this case, 15 into 3 is 45, and that's going to be returned to you. So this is actually very useful, that you can go ahead and change the values of any of these tensors which are feedable and use them for testing and whatnot. But the important thing to note is that if it's a placeholder, then you have to provide the value. If it's not a placeholder, then depending on the value of this variable feedable, whether it's true or not for that particular tensor, you can modify or put in the values well when you're calling ses.run. Okay, so lazy loading. Let's see. So the idea out here is that we create an object only when it is needed. So in an example, when you're this is the example of normal loading, where you would have x and y as variables, and then you would define an op z is equal to tf.add xy. So that node is created within the within the graph before you try to execute the graph by calling ses.run, right? And then with when you're trying to run it, you'll first create the session variable, and you'll first instantiate the session, I should say, and ses.run, you'll initialize all these variables. So now after this, the value of x is 10, y is 20, and let's try to put these events in the for tensor board. So you put in this line tf.summary.filewriter in the location you want, and now when you call this multiple times, like the 10 times you are trying to call out here, and you run this, what's going to happen is it's only going to add one add node in the graph, because you are calling this op. This op is already defined. Now when you are running it, executing it, it's just going to keep on adding the value of x and y. And within the tensor board, there's going to be just one node for tf.add, because that's what we explicitly defined before we started running it. Now in lazy loading, what you are trying to do is, instead of defining z out here, you will call ses.run tf.add xy. So you don't put the z which we were talking about earlier. You just put in that op during execution. Now what will happen is you'll still get the right answer. It will still show you 10 plus 20. Now the problem is that in the normal loading, this add node was added just once in the graph, right? And in lazy loading, what ends up happening, this was the graph before execution, and as you start executing it, what will happen is you'll have multiple add nodes. So if you were to print out the graph using this method, get default graph as graph default, as graph def, in the normal loading situation, you'll just see one node add, whereas with the lazy load, you will see multiple nodes. So now you can imagine that if this loop was called like 1,000 times, your graph will just bloat up, and this is going to cause problems, and it will be like really hard to like pass the graph around, save it, all that becomes hard. So this is like one of those things which is not actually a bug per se, but it's a bug because it can cause problems with bloat, etc. So the way you do get around this is to separate the definition of ops from like computing and running ops. So what do we mean by that? So one of the things is when you're defining an op, let's say in the case of a small model, let's say we have the value of x, and you want to calculate x into w as your model prediction, right? And let's not even worry about b. So if we have a function which is called get prediction, right? And now within that function, let's say the very first line out there, you're trying to define the variable for w, because this is what's going to be training. So if you say tf.variable, provide a shape for value out there, a shape for w out there, and the next line would be y prediction is equal to x, which is the input, multiplied by w, right? Now, if you're calling this function again and again, what will happen is you are that first line, which is that definition of the variable w, is going to be called multiple times, right? And you don't want that. So you want to have, the way you should structure your code is, in one place is, let's have the variables defined, the various definitions of ops, and in other place the computing op, which is in this case would be like x into w. So that would help you, if you do that, you're not going to run into this issue. And structure your code would be to use Python properties. So what we want to do out here is, let's say we have the various functions, which is prediction out here, and we call the add property on it. So now what you are able to do is to call, let's say m is an instantiation of the model. You can just say m dot prediction without the parenthesis. So you can use it as a instance variable. So what happens out here is, you first define those internal attributes, self dot underscore prediction, and when you init the model, that is none. Let's optimize is also none, and error is none. Let's talk about these three ops, and then we will see how this works. So when you call add property on this function prediction, the first thing we are checking is if not self dot underscore prediction. Then we are going to go ahead and get the data size, target size. We are going to define weight. So you're going to be calling tf dot variable, and so you're going to be defining weight. You're going to be defining the bias with tf dot variable again out here. And then you're going to be adding an op incoming tf.matmul self.data, comma weight plus bias. And the very first time you do that, when this is none, we are going to be hitting this code block, and you are going to be adding this. You are going to be now self dot underscore prediction is not going to be none after we are done with this, because it's going to be assigned the op tf dot nn dot softmax incoming. Okay, and if it is not none, we are going to be returning this instance variable self dot underscore prediction. So the thing which is inside this code block is only going to be called once, the very first time you call model.prediction. And after that, it's only going to be returning this self.prediction, which is a handle to this op. Okay. Similarly, for optimize, you do the same. If not self.optimize, you will call the loss, cross entropy in this case, and add this op in the graph. You're going to instantiate an optimizer, and self.underscore optimize is going to be optimizer.minimize loss, the cross entropy loss. So this is the node that's going to get added in the graph. In addition to optimizer, cross entropy, all these nodes are going to be added at the very first time. And then afterwards, if you were to call model.optimize, it's only going to be returning a handle to this part node in the graph, right? So optimize.minimize cross entropy. So let's see what happens, because what we are going to be doing is to be calling optimize multiple times. So let's just slowly go into what happens so that we can figure out the flow. So when the optimize is called the very first time, all these nodes are going to get created. Okay, and within this you will see that tf.log self.prediction is being called. So very first time after we initialize all the variables, and let's say you call optimize after the init. So once you do the init, you have the data set, the target set, everything else is none, right? And we are here, we are optimized, we are in, we just called optimize. So now we see self.prediction. Now self.prediction is none at that time, very first time. So we are going to be calculating this stuff. We are going to be adding the weight, bias, incoming nodes at that time, and we are going to be calculating those. Um, and then we are going to have the tf.nn.softmax incoming. We are going to calculate and we are going to return the value. We are going to return the predictions. It's going to calculate the cross entropy. It's going to create the optimizer the very first time. Now it's going to run this op, self.optimizer.minimize cross entropy. It's going to run it the very first time. And what TensorFlow will do is once it runs the loss, it's going to do the backprop for you, which you get for free again. And then it will look at all the variables in the graph which contribute to this loss. And so when you go to prediction, it will see that, okay, weight is a variable, bias is a variable, and it is going to update weights and biases after the very first time you call that, right? So you'll have a little bit of an update. So now the weight and the biases are different after this first optimizers run than it was before, right? Now let's see what happens the second time. So now when the optimize is called the second time, self.optimize is not none. So we are going to return this. Self.optimize got saved with this op out here. So in the graph, this node is going to be already present. So TensorFlow is going to look at this and see, okay, well, I need to calculate optimize.minimize cross entropy. And it's like, I have the node called cross entropy. I have that node also out here because that's where it got added the very first time. It's going to go and do the reduce sum on self.target, which we have. And then it's going to look for self.prediction. Self.prediction is also there. The node is already there. It is not none. And it will see that, okay, it needs to calculate nn.softmax on incoming. Incoming node, it will find to be the matmul self.data comma weight plus bias. Now this weight is different from the very first time because we just made that very first update after the very first time we called optimize, right? So now it's going to calculate the incoming, and that's all it needs to figure out the graph. And then it's going to do the same thing again. Now it knows it will see that, okay, it just needs to minimize that. It doesn't need to get here because it's not going to be calling that tf.train RMS prop optimizer again because it doesn't need to. It already finds everything in the graph. And then it's going to minimize and update the weight. So this is how it is going to keep on going. So using properties will help you structure your TensorFlow code even better. So I think we are going to go into this example in the next lecture. So till then, thanks a lot.